All right, hello everyone. Welcome to my channel. This channel is for the purposes of education, and we generally look at theories of everything, all-encompassing theories, paradigm shifters, um, obscure and esoteric um, cosmologies and philosophies that can help you become more well-rounded and more grounded. And today is our 352nd video on Dewey B. Larson and his reciprocal system of theory. And the reciprocal system of theory was originally originated in about 1930 by Dewey B. Larson. He eventually wrote up his two fundamental postulates in the late 1950s, and from there took his postulates and through a process of deduction derived a theoretical universe, how everything would look if his postulates were true. And then he took his theoretical universe and he kind of, in his books, he compared his theoretical universe with that of the legacy scientists. And the results were, similar to, maybe the 20th century, early 20th century legacy science, of where they basically affirmed everything that Newton had said, except for the so-called relativistic areas, the areas of the very small, the very fast, and the very large. And in those areas, the Newtonian mechanics broke down, and Einstein stepped in and provided these relativistic equations and philosophies to bridge the gap. But so Larson kind of does the same thing, but he bridges the gap in a much more convincing manner than Einstein, and a much more holistic and conceptually based. Einstein, a lot of times, just he can give you some math that he borrowed from somebody else, but he doesn't tell you why these things happen, why he's imposing these equations on this particular circumstance. Larson is providing, in some cases, the same math, but he's providing the underlying concepts because he's dealing with a universal theory that you can apply to anything. And that's why he calls it the reciprocal system of theory. It's a system. If you know how the system works, then you can apply it to whatever subject you like. If you are, you're a chef, you can apply it to the reciprocal system of, chicken cacciatore or whatever. You can apply the reciprocal system to any subject and come up with fruitful answers. So we are, let me just basically say that the basic idea behind the reciprocal system is that we live in a universe made out of motion. Not matter and not energy, not force, but motion. In fact, E equals mc squared, Einstein's equation, energy equals matter times the speed of light squared, shows you that, well, energy can be converted into matter and vice versa. If that's the case, then that means that by definition, neither one of those things can be the most fundamental thing in the universe. If one can be converted to another, there must be something that underlies both of those things. And you might want to instead look at the c squared part. That is the speed of light squared. That is much closer to the composition of the universe, which Larson says is motion. In particular, it's what you would call a scalar motion. That's a motion that has a magnitude, but it has no specific direction. And that can be visualized using a balloon with dots on it. If you blow up the balloon, all the dots are moving away from each other, but in no particular direction. And if you suck in the balloon, all the dots are moving toward each other, but in no specific direction. And the Hubble telescope discovered that all of the distant galaxies are also moving away from each other, but in no specific direction. And Larson calls that clock time and clock space. The clock is also another example of a motion that is lacking direction. The clock is always getting later and later and later, but in no specific direction. That is a scalar motion. And clock space to go along with clock time. Well, first, let me just say that motion in Larson's formulation is the relationship between space and time. So that sets up a reciprocal relationship between space and time, hence the reciprocal system of theory. And that space and time don't really exist independently. They only exist together in motion. Motion is really a fraction with time or space as the numerator, space or time as the denominator, and such as speed. Speed is space over time. I drove the car at 14 miles per hour. 14 miles of space and 1 hour of time. Space over time. And all other scientific quantities are likewise relationships between space and time. And as reciprocals of one another, space and time both have the same qualities. And so if we've got this clock time, the clock is always getting later and later and later, then we're also going to have what Larson calls clock space. And that is a motion that is a scalar motion in space, which can be modeled using this balloon with dots on it. If you want, you could add another dimension, and you could use something like raisin bread that you put in the oven. As the bread rises, all of the raisins are moving away from each other, but in no specific direction. And Larson refers to that as clock space. The space is always getting farther and farther and farther apart. And then there is what Larson calls coordinate space and coordinate time. This is 3 dimensions of space and 3 dimensions of time. XYZ coordinates in space, and possibly something more like IJK coordinates in time. And this is a kind of a specialized case of space and time, which occurs within a gravitationally bound system. And then we have also that time and space come in only discrete units. There's a minimum unit of time and a minimum unit of space. If you don't have a full unit, then you don't have anything. You have to have a full unit of space or time before you have that entity. And those are very small, but they are still significant. You have to have a 4.56 times 10 to the minus 8 meters, which is like 1/500,000th of an inch. And then for time, you have 1.52 times 10 to the minus 16 seconds, which is 6.576 quadrillionth of a second. So very small, but nonetheless, you have to have a full unit of time or space before you have that entity. Now, if you have 1 unit of space in 1 unit of time, 1/1, space over time, which we remember we said was speed, then you have the speed of light. Speed of light is 1 over 1 equals 1. Larson calls the speed of light unit speed, and that is the background of this universe. This is what he calls the 0 point, or the state of rest of the universe of motion, is outward motion in all directions at the speed of light. So that also gives more credence to this E equals mc squared kind of idea, that the fact that energy can be converted into matter and vice versa eliminates both of those things as being the fundamental thing, but sheds light on the c squared part, the speed of light, as being more fundamental. And in a universe of motion, it makes sense that motion is the fundamental thing that is there before everything else. And so that speed of light is the background or the reference datum, and it also means that half of the universe is moving faster than the speed of light, as well as half that's moving slower. The legacy scientists only understood the half that's moving slower. Einstein himself said that the speed of light is the maximum speed of the universe, whereas in Larson's formulation is the midpoint of the universe, and an entire half the universe is defying Einstein's dictum. And fortunately, the relationship between the two halves of the universe, which Larson refers to as the material sector, slower than the speed of light, and the cosmic sector, faster than the speed of light, is a reciprocal relationship. So if we know, which we claim to do, to know about what's going on in the material sector, then we automatically also know what's going on in the cosmic sector, because it is reciprocal. All we have to do is reverse the roles of space and time. So in the material sector, you've got coordinate space and you have clock time. But in the cosmic sector, you have coordinate time and clock space. And it goes on from there. But basically, that's Larson's first postulate. His second postulate is that the universe conforms to the relationships of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Now, we went through an article last week talking about a revision of those two postulates, especially the second one, where projective geometry was plugged in instead of Euclidean geometry, as Euclidean geometry is just a subset of projective geometry. And a few other words were tweaked. And that was an article that was done by Dr. Bruce Peret, who is one of the main revisers of Larson's, after Larson's death in 1990. Peret came on the scene and I think did a great job of really being in the spirit of Larson's reciprocal system, but at the same time updating and making strategic changes to the reciprocal system that allowed it to be a little bit more stand the test of time. Larson admitted that he was fallible, that he was subject to error. He believed that the postulates themselves were correct, but that his application, his derivations may be incorrect. And so Bruce Peret has about 9 articles here that he calls RS2, Reciprocal System 2, or the reevaluation of the reciprocal system. and he numbers them 101, 102, 103, and today we're about to start number 106, which is called Dimensions and Displacements. Okay, we'll get started with this. It'll probably take us 2 or 3 days to get through it. In the reciprocal system, everything is based on scalar motion, which is simply a ratio of some magnitude of space to some magnitude of time. This ratio constitutes a dimension of motion, where there are 3 possible states, which he calls orientations in a different context. The 3 possible states are unity, where the magnitudes of the aspects of space and time are equal. This is the default condition of a dimension of motion, which Larson refers to as the progression of the natural reference system. So this is the 1 over 1 equals 1 idea of the speed of light. If you have 1 unit of space and you have 1 unit of time, then you have unity. And it's right here, he says, where the magnitudes of the aspects of space and time are equal. At that place, space and time both equal 1. 1 unit. And so this is the speed of light, which Larson refers to as the progression of the natural reference system. Since unit motion equates to the speed of light, the default motion of the universe is outward at unit speed. In other words, everything in the universe wants to fly apart from everything else at the speed of light, just for the heck of it. No energy required. Okay, now that is the first orientation of the ratio between space and time. Now, then the other 2 are when space and time are not equal. So obviously one of them is going to be where space is greater than time, and the other one is going to be where time is greater than space. So we'll go to those right now. Speed, where the temporal magnitude, or the time magnitude, is larger than the spatial magnitude, results in motion that is less than unity. Speed forms our conventional frame of reference where everything is moving at sublight speeds. Larson uses the ratio of space over time to represent speed, which is the conventional way to represent velocity. To move some amount of space per some amount of time. Now, the only difference between space and velocity is that speed and velocity is that speed is a scalar motion with no direction attached to it. Energy is the third option, where the spatial magnitude is larger than the temporal magnitude, results in a motion that is greater than unity, greater than unit speed, greater than the speed of light. Larson uses the ratio of time over space to represent energy, which is the conventional concept of mechanical work. How much time does it take to move something a specific distance? So that's energy, time over space. It took me 2 hours to move that thing 1 mile. 2 hours of time in 1 hour of space. Time over space, energy. Over unity, faster than light speeds are not directly observable. So this energy, from the cosmic sector, faster than light speeds are not directly observable from our conventional reference system. This is our stationary reference system where we are positing that something is actually not moving. But we can observe how energy changes space through the use of a device known as force fields. These lines of force are the lines of energy per unit distance. Time over space per distance. So time over space to the second power. Time over space over space. So that is force. Force is time over space to the second power. And you can kind of think of these force fields in terms of your balloon analogy. So you're blowing up the balloon and all the dots move away from each other. When you suck in the balloon, all the dots move toward each other, but in no specific direction because they're all moving toward each other. And so, you know, there's no specific direction assigned to that until you arbitrarily choose a reference point. I'd like to also point out that not only are the points, the dots on the balloon moving toward each other, but even the spaces between the dots are also moving toward each other. But at a certain point, you can arbitrarily decide that, okay, one of these points I'm going to say is not moving. This is my reference point. This is what is not moving. And then, voila, you have distances then. You have directions then. You can determine, okay, this dot is moving in this direction toward me. This dot is moving in this direction toward me. And that straight line direction from one dot to another is analogous to what he's talking about here with the force fields. It appears as if there is a force field between the two dots because they're moving toward each other. But there isn't. It's only the result of assigning a reference system. So the scalar motion itself does not bring out a force field. The force field is a fiction, which is the result of you fixating a reference point, an arbitrarily motionless point, because that dot that you're choosing as the reference point is actually in motion toward all the other dots, but you're negating that and you're just saying, no, this dot is motionless. And so then all of a sudden, all of the other dots are moving toward that dot. And it appears as if there's like some kind of force field that is bringing about that motion. But that is a fiction. Okay, so when a dimension is at unity, nothing manifests, as it is equivalent to the expansion of the cosmos at the speed of light. In our conventional reference system, the first unit of motion is speed, creating a material structure such as a particle or atom. The first unit of motion can also be energy, which also creates an inverse particle or atom that Larson calls cosmic matter, which is conventionally called antimatter. So in the material sector, you have atoms, particles, atoms, and molecules. In the cosmic sector, you have cosmic particles, atoms, and molecules, or what conventional science calls antimatter. This difference between speed, space over time, And energy, time over space, defines the two-sector approach of the reciprocal system. The material sector, which contains speed, space over time, reference to clock time. So clock time is the reference there in the material sector. So you have basically coordinate, space, and clock time. And the cosmic sector, which contains energy, time over space, referenced to clock space. Okay, I think we're going to stop right there, and then we will take over tomorrow with the section that starts number of dimensions. So we just kind of defined here this first dimension. When a dimension is at unity, nothing manifests. If in a universe of motion, the first unit of motion is speed, and in the material sector, and energy in the cosmic sector. And so he's going to talk about dimensions here. One thing that we have to keep clear is there's really, in the reciprocal systems, kind of two different kinds of dimensions. There are dimensions of motion, and there are dimensions of scalar motion. It takes dimensions of space, like coordinate space, and then dimensions of motion, or dimensions of scalar motion. It takes 3 dimensions of space to define 1 dimension of scalar motion. So that is a sticking point that it takes a while to overcome, or to surmount, is that you have dimensions of space, like coordinate space, 3 dimensions of space, but it requires 3 dimensions of space just to define 1 dimension of scalar motion. So use that analogy of the expanding balloon again. The expanding balloon occupies 3 dimensions of space, but that is just 1 dimension of motion. That is, space is always getting farther and farther and farther apart. And we really are only able to observe 1 dimension of scalar motion at a time. So we are bound kind of in that reference system. But there are 2 other scalar dimensions that we can perceive in a limited way. Okay, we'll get into that starting tomorrow. In the meantime, thanks for tuning in, and have a great day.